So here's the example. In this example, we are going to go from the original distribution to the conditional distribution. We will use the formula and compute it. Okay, so I'm just to illustrate the definition, just to give you an example. Okay, so throw a die. You have the uniform distribution in the set 1, 2, 3, 4, 5, 6, and we have assigned the distribution, okay, 1 by 6 to each, and you have the event E. Event E is 2, 4, 6. Let's say it's a even number, right? So you've got an even number. So P of E is easy to write down. It's 1 by 2. You know that. So if we move to the conditional probability space given E, you have 2, 4, 6 as your sample space, and then you have all these events inside it. You could have 2 given E. What is the probability of 2 given E? It's the probability of 2 intersect E divided by P of E. And what is 2 intersect E? 2 intersect E is 2 itself. So probability of 2 by probability of E. So that's 1 by 6 plus, but divided by 1 by 2, that's 1 by 3. Okay. So it's just, examples to illustrate the formula. P of A given B is P of A intersect B divided by P of B. How do you use that formula? So if P of 4, you have to do this calculation. If you were to do P of 1, okay, which is not a valid event in your sample space, so what will happen is when you do the intersection with E, it will go to a null set. Okay, when you go to a null set, automatically the probability will go to 0. So the conditional probability space, the definition, interacts very nicely with the original probability space. Even if you go wrong in the event, you pick an event in the conditional space which is not even there, right? It will deal with it very smoothly. With the intersection with E, will just kill it. It will make it null space. Okay, so you don't have to change any formula or anything. Okay, so it's a very nice, neat interaction between the conditional space and the original space. Similarly, 3 given E and 5 given E also 0. 4 and 6 given E are 1 by 3. And you can also calculate more events. So what about 2, 5 given E? Okay, so this one again. So you might say, okay, 2, 5 is not a valid conditional event, but that doesn't matter. So this A is any event in the original space, right? So you can always define a conditional one for that. You can take 2, 5 intersect with 2, 4, 6, right? So what would happen here? You would get P of 2, 5 intersect with 2, 4, 6 divided by P of E, and that intersection is just the same as P of 2, right, divided by P of E is 1 by 2. So 1 by 6 by 1 by 2 is 1 by 3. Okay, so you get the same answer. So what about 2, 3, 4? 2, 3, 4, when you intersect with 2, 4, 6, you have 2 size intersection. So that's a probability of 2, 4 in the original space. That's 2 by 6 by 2 by 3. I'm sorry, did I get that right? 1 by 3 by 1 by 2, I'm sorry, 2 by 6 by 1 by 2, so that gets 2 by 3. So that's also fine. Okay, so this is how you calculate given definition like that. So you given an original space, you given an event E, you're conditioning on that event E. This is how you calculate the probabilities. Okay, so this is very rarely will you use conditional probability like this. Okay, so let me be the first to tell you, it's very unlikely that only in quiz problems and practice problems you may do this. In reality, the way conditional probability will occur is in a sequence of steps, and you will condition on the first step and go to the second step. Condition on the first and second step, go to the third step, like that. Okay, so that's how you will condition over and over again. So let's see maybe a simple example of that. Okay, a very nice example that one can give, a very simple two-step process, is these two urns with colored marbles. Okay, so instead of just blindly writing down, I thought I'll make a picture here with two urns and a bunch of red color marbles and blue color marbles. Okay, what is my experiment now? I'm going to pick an urn at random. Okay, notice there are two steps here now, right? So you first pick an urn at random, and then you pick a marble at random from the chosen urn. Okay, it's not that all of them are put together and I pick one at random. Then I have only one action. Here I do it in two steps. First step, I pick an urn. It could be urn 1 or urn 2. That I do at random. Then once I pick an urn, I go in and pick a marble from that urn at random. Okay, so that's what I do here. And notice how easily you can do these conditionals. So notice how the conditionals work out. Okay, you don't have to write sample space, and you can try to do all that, but it's quite easy to see. So when you condition on urn 1, what are you conditioning on? The urn you picked is urn 1. So you've gone into urn 1. So the sample space, the conditional sample space, is very clear. It's just picking randomly a marble from urn 1. That's your conditional sample space, isn't it? You don't need to worry so much about the entire initial sample space. It's enough if you write down the conditional sample space, and you can directly find probability of red given earn 1. There are 7 red marbles here, total of 13 marbles. So, probability of red given earn 1 is 7 by 13. Probability of red given earn 2 is 5 by 13. Again, right? Notice how the conditioning is so natural to do. You move naturally to the conditional space, and the conditional space is very, very easily laid out for you. Okay. Probability of blue given earn 1 is 6 by 13. Probability of blue given earn 2 is 8 by 13. So, notice a curious thing, these two are adding to 1. These two are adding to 1. Is this an accident? Is this an accident, or is it guaranteed by the axioms of probability? Okay, I would say it's guaranteed, isn't it? Red or blue in the conditional probability space, when you pick, you should either get a red marble or a blue marble, right? So, those two things are the entire sample space of outcomes. So, the probability of those two together, they are disjoint also. Those two together should give you 1. Okay, likewise, the probability of these two together should give you 1. These two are complements in the conditional probability space. These two are complements. Maybe I should write it a bit clearly. Complements in the conditional space. Okay, so the probabilities better add up to 1. Okay, because you know the conditional space is still a probability space, isn't it? It has to respect its axioms, it has to respect all the properties that you have for the original probability space, isn't it? Complements have to be 1 minus of each other, the disjoint unions have to add, A union B has to be P of A plus P of B minus P of A intersect B. All of those properties have to be satisfied even in the conditional space, and you can use all of that and do it. Okay, and you can see how naturally the first step and second step comes, and how you naturally can use conditional probability without worrying so much about sample space and all the theory and the equations. Okay, so this is the skill I was talking about. This is the comfort I was talking about that you need to pick up when you work with conditional probability. Okay, so let's move on and see a few more examples, maybe slightly more complex than the previous ones. Okay, and these kind of examples also illustrate the power of conditioning. You'll see if you weren't conditioning, you'll have to do all sorts of things and keep track of everything. And when you condition one after the other, things become so much easier. Okay, so here's a class with 15 students and people from multiple states. There are 3 states in particular. There are 4 from one state, 8 from another state, which we call state 2, and 3 from state 3. Okay, so 3 students are picked. 3 different students are picked at random, usually one after another, and that's something you can assume. Okay, so you pick one after another, 3 students at random. The question asks, what is the probability that the selected 3 are from state 1, state 3 and state 1 again in that order? Okay, so the first one you select is from state 1, next one you select is from state 3, next one is select is from state 1 again. Okay, now if you were to do it without conditioning, you'll have to do all sorts of things, and you can see there are multiple steps here, right? It's not just 2 steps. There is the first step where you picked someone, and then something would have happened. And then conditioning on that, you have to move to the next step where you will pick one more person, and then conditioning on that, you will go to the next one. Okay, so the way you think of this is you write it as 3 events. A1 is first student is from state 1, then you write A2, which is second student is from state 3, and then A3 is third student is from state 1 again. Okay, the question is asking for probability of A1 intersect A2 intersect A3. Okay, so let me put a bracket here and think of A2 intersect A3 as one event. This is my B. Okay, so I will write this as, oh sorry, this is my, I don't know, this is my B, okay, and this is my A. Okay, I want to write this as probability of B times probability of A given B. Okay, now what is B now? B is A1, right? So probability of A1 times probability of A2 intersect A3 given A1. Okay, So notice how I wrote this out. The second event is this sort of bigger combination A2 intersect A3. It's still big. It's not just one event. This is intersection of two events. Now this P of A1, notice it's very easy to do. Right? What is A1? First student is from state 1. It's just the first student you're picking. There are 4 from state 1, 8 from state 2, 3 from state 3. What is this probability? It's 4 by 15. Anybody can tell you that. Okay. Now the question is, what do you do with this guy? Probability of A2 intersect A3 given A1. Okay. This looks a little complicated, but remember, this is in the conditional probability space given A1, but it is also a probability space. I can further do the same conditioning trick that I did before. Okay. So I'll write down how I do this. This guy can be written as probability of A2 given A1. Okay. Notice this is like my, this is like my new B, and this is like my A. Okay. So I can write this probability as probability of B, but notice it's not just probability of B. Why? Because I'm in the conditioning on A1 space, right? I've gone to the smaller space, so I have to write this as probability of B given A1, right? So that is A2 given A1. Okay. Next, what do I do? After that, I can write probability of A3 conditioned on A2 should have already happened. Okay. A1 has already happened. A2 also should have already happened. So what you do there is A1 intersect A2. Okay. So this is a little bit of a trick here. So notice what I'm doing. I'm in the initial probability space. I did the first round of conditioning, but then I found I still have an intersection going on. A2 intersect A3. I have a step 2, and then I have a step 3. So once I move to the conditional space, I can do a further conditioning. Okay. For that, I say A2 first. I split it as A2 intersect A3. So I have A2 given A1 times A3 given A1 intersect A2. Okay. So this is sort of a formal result that you can keep repeating this conditioning. This is, if you look at your book, this is stated as a formal theorem and all that. I didn't want to do it in a formal way. I just wanted to introduce it to you informally. Okay. So notice how easy it is to keep conditioning. I have A1 intersect A2 intersect A3. It seems like a complicated problem. I have to write down all sorts of possibilities, but I can proceed by conditioning. Look at the divide and conquer approach. I can do A1, A2, A3 given A1, and then this A2 intersect A3 is further conditioned. And how easy it is to do. Notice how easy it is to do this problem. What is A2 given A1? A1 has already occurred, which means what? The first student has been chosen, and that person is from state 1. So if A1 has already happened, then what are the remaining students? What is the sample space? Given A1, there are 3 from state 1, 8 from state 2, and 3 from state 3, isn't it? So in the conditional space given A1, you have 3 from state 1, 8 from state 2, and 3 from state 3. And A2 is asking, what is the event that A2 is the event that second student is from state 3. So that's going to be 3 out of 14. Notice how easy this calculation is. You're not having to write down all possible combinations of picking 3 from 15 and then choosing out one after the other. You can just go step by step, and it's very easy in every step, right? So 4 by 15 times 3 by 14. Okay. And then notice the last one. What is the last one? A1 intersect A2 has happened already. If A1 intersect A2 has happened, what does it mean? The first student has chosen, that was from state 1, and then the second student was chosen, that is from state 3. Okay. So now after A1 intersect A2, so given A1 intersect A2, you will have 3 from state 1, 8 from state 2, and 2 from state 3. And what's your probability of that? Probability of A3, which is picking someone from state 1, given that the first 2 were picked from state 1 and state 3, it's 3 out of 13, isn't it? 3 out of 13 in total. So that's the answer. Okay. So if you had to enumerate all the possibilities of picking 3 students from 15, imagine that's a lot of possibilities, okay. So I'm not saying it's difficult to do, but still take much longer time, and notice how conditioning has simplified the work for you, okay. So you did P of A1 times P of A2 intersect A3. There's a little bit of thinking here to do about how I further condition. Say I went into a smaller space and then I further condition from there. Nothing stops me from doing that. That's also a valid probability space. If I have an intersection of 2 events there, I can further condition. Anytime I have an intersection, I can condition. That's the idea. But I'll condition in the conditional space. And when you go further conditioning, the further conditioning becomes an intersection because both of them have happened. Okay, so that's the slightly tricky idea. Think about that. It will be clear to you. Okay, so this probability finally, after breaking down the whole thing, has worked down to 4 by 15 times 3 by 14 times 3 by 13. You can simplify this if you like, you will get an answer. Okay, so hopefully this showed you the power of conditioning. I think this, to me, this is a very nice example which illustrates how powerful it is to condition. If you did not condition, you'll have to do so much work. Here conditioning just let you do step by step by step, and in every step you are doing a very simple sample space. Okay, the conditional space is very simple to deal with. On the other hand, the overall space seems much more complicated. Okay, hopefully this was useful, and hopefully you'll see more problems like this in your assignments. Okay, so the last example I want to do in conditional probability is this sort of deceptive problem where people give a lot of answers which are intuitively very happy about, but the word conditional and the word probability given something mean certain specific things, and in that case you'll see the answer here is a bit surprising. Okay, so let's look at this question. There's a family with 2 children, and the question that's asked is, what is the probability that both are girls, both the children are girls, given that at least one is a girl? Okay, notice the condition, notice the first thing that I always see when somebody asks this question is the word conditional is dropped. Okay, that from a mathematical point of view, it's sort of unsettling, but I mean you can see that it's given something, right? So obviously the probability that they mean here is conditional probability. What is the conditional probability that both are girls, given that at least one is a girl? Okay, notice that subtle thing of at least one is a girl. I mean it includes girl boy, boy girl, and girl girl. Okay, so it's sometimes people just miss this, and it seems sort of clear that if you say one is a girl, the other has to be a girl, but it doesn't say one is a girl, right? So it says it doesn't say exactly one is a girl, right? So if you say one is a girl, it sort of makes sense that the other is a girl with probability half or something like that. But here it seems like what you're conditioning on is not exactly one is a girl. It's you're conditioning on I mean you can think about what I'm saying here. So if you have exactly one girl, the other cannot be a girl, right? So it goes to probability 0. It's no problem there, and it doesn't say one. So the conditioning is a bit tricky. Think about why that is true. Okay, so the sample space here is basically girl comma girl, both are girls. The first one is a girl, second one is a boy. The first one is a boy, second one is a girl, and then both are boys. Okay, these are the 4 possibilities in this problem, and we'll assume uniform. Okay, so it doesn't mention any distribution, so we're going to assume uniform distribution. And what is this event B that we are interested in? At least one is a girl. Okay, so if at least one is a girl, there are 3 outcomes that qualify under at least one is a girl. So this is at least one is a girl. Okay, so this is that event. Okay, so now the question is, what is the probability that both are girls? So the question that's asked is probability of girl comma girl, this event given B. Okay, so this is going to be probability of girl comma girl intersect with B. So what is girl comma girl intersect with B? Divided by probability of B. girl comma girl intersect B is girl comma girl itself, right? So there's nothing in this intersection. By probability of B is 3 by 4. So you have girl comma girl is 1 by 4 by 3 by 4, and that's 1 by 3. Okay. So out of the 3 cases where at least one is a girl, both are girls with probability 1 by 3. Okay. So slightly counterintuitive. A lot of people, depending on the wording, just want this answer to be half, right? It seems like I'm saying what is the probability that the next one is a girl or something like that. It's not the same. It's a subtly different question, and a lot of probability questions become confusing, particularly with conditional probability, for this reason. So when you have this kind of complexity, it's better to write down the sample space clearly. Okay, don't try to work without the sample space, without the conditioning event and all that. You will get into trouble here. When you have problems of this nature where the wording is a bit confusing, it's better to write down the sample space, and you'll be always okay. Okay, so that's the end of this lecture. This was a very important lecture. It introduced a slightly confusing and often misused idea of conditional probability, but also hopefully it showed you the power of it. If you can use it correctly, it can give you fantastic results in wonderful way, and it's very, very powerful idea, very crucial idea for the entire program, I would say. Okay, thank you very much.